Water. It's one of the most powerful forces on our planet. But what if we could predict its most chaotic, destructive behavior with, well, perfect accuracy? Today, we're going to dive into a really fascinating study that pits some advanced AI against an age-old engineering problem. So the big question is, can artificial intelligence finally tame a flood?
All right, let's get into it. To really understand why this is such a big deal, we first have to get a feel for the raw, destructive power that hydraulic engineers are trying to wrestle with every single day.
And believe me, that is not an exaggeration. When you have massive amounts of water rushing over something like a dam or a spillway, it builds up an absolutely immense amount of kinetic energy. We're talking about a force that can literally rip apart the very steel and concrete structures designed to hold it back.
Now, there's a technical name for this destructive process. It's called downstream scour. This is what happens when that powerful jet of water slams into the riverbed at the bottom of a dam. It basically acts like a giant liquid chisel, just digging away and eroding the earth and rock. And that can undermine the entire foundation of the structure. If you don't stop it, the whole thing could eventually fail.
So how do you fight back against that kind of force?
Well, engineers figured out you don't just build a bigger wall, you build a smarter one. Let's take a look at the really clever design they came up with to solve this, the stepped spillway. You know, the idea is actually pretty brilliant in its simplicity. Instead of having one long, smooth slide that just lets the water build up speed, a stepped spillway is basically a giant staircase for water. As the water tumbles down from one step to the next, it churns and foams up, breaking apart and getting rid of its kinetic energy all the way down. This means the force at the bottom is way, way lower. That prevents the dangerous scour, and hey, as a nice little bonus, it also means you don't have to spend as much money building massive reinforcement structures. But, and there's always a but, right? This is where a simple-looking design gets incredibly complicated. It turns out that depending on just how much water is flowing, its behavior can change dramatically. The water actually organizes itself into three totally different types of flow.
First up, when you have a low amount of water, you get something called Nappe flow. The easiest way to picture this is as a series of small individual waterfalls. The water just jets off the edge of one step, flies through the air, and lands on the next one, leaving these little air pockets in between. It's pretty orderly, pretty predictable.
Now, let's crank up the volume to a high discharge. When that happens, the physics completely changes. You get what's called skimming flow. Here, the water is moving so fast that it just glides right over the very tips of the steps. It's like it creates its own smooth surface to flow on, a pseudo-bottom. It basically turns the whole thing into a fast water slide, and all this swirling water gets trapped on the steps underneath.
And that brings us to the real problem child, transition flow. This is the messy, chaotic state that exists somewhere in between the other two. It's just a highly turbulent, unpredictable mess of air and water, and it has bits and pieces of both Nappe and skimming flow. It is by far the hardest state for engineers to model and predict.
So why is this such a huge deal? Why does predicting this stuff matter so much? Well, because the entire safety and efficiency of the spillway design hinges on knowing which flow type is going to happen and when. Engineers have to know exactly how that water is going to behave during a flood so they can build a structure that can handle it. Getting this prediction wrong isn't just a small mistake. It could be disastrous.
For years, accurately predicting these flows has been a massive headache for traditional physics models. But now, there's a new player in the game. Let's see how this challenge sets the stage for a really cool AI experiment. Now, this isn't the first time we've thrown AI at this problem. Older models, like artificial neural networks, or ANNs, have had a crack at it. But this new study pits them against a new generation of AI challengers, 3 ensemble models called AdaBoost, XTrees, and XGBoost. The big difference here is how they work. Think of them like a committee of experts. They combine the results from tons of simple little models to come up with one single super accurate prediction. So to put these AI models to the test, researchers used a data set from 126 real-world hydraulic lab experiments. And to make sure the test was really tough, they didn't just run it once. They actually split the data in 2 different ways. One split gave the AI lots of data to learn from and a little bit to test on. And the other split did the opposite. They really wanted to push these models to see how they'd perform under pressure.
The process itself is pretty standard for machine learning. So here's the game plan, right? Step 1, you pick your AI models. Step 2, you train them on some of that lab data, letting them chew on it and learn the patterns. Step 3, you unleash them on the rest of the data, stuff they've never seen before, to see how well they can predict. And finally, step 4, you line them up and compare their accuracy to see who the real champion is. All right, the moment of truth.
After all of that training and testing, which AI model was actually smart enough to understand and predict the chaos of flowing water? Let's unveil the results.
And the results were, to be honest, just stunning. This table shows what's called the R-squared score. It's basically a score for accuracy, where a perfect 1.0 means you absolutely nailed it. In that first test, the old AN model did great, scoring a 0.9996. But then, just look at AdaBoost.
That's right, a perfect score, 1.00000. It got a flawless prediction. On the test data, it correctly identified the flow type every single time, without a single error. That is just an incredible, almost unheard of level of accuracy for modeling something this complex.
And you can literally see the proof right here. These are heat maps of the prediction errors. Simple rule, blue is good, meaning fewer errors. You can see on the left in that first test, AdaBoost is just a solid block of deep blue, practically zero errors. And even on the right, in the tougher tests with less training data, it still has the least error, especially in that really tricky transition flow where the other models started to stumble. So the big question is, how did it do it? What was its secret? Well, using a technique called SHAP analysis, the researchers were able to basically pop the hood on the AI's brain to see what it was thinking. And they discovered that the AI had figured out the single most important factor is something called HC/H. It's a simple ratio between the water's depth and the height of the steps. The AI basically reverse engineered the core physics all by itself.
Okay, so this is way more than just a neat computer science experiment. Let's talk about the big picture here and what this all means for the future of engineering. And this is maybe the most important part. The researchers themselves pointed out that the winning model, AdaBoost, isn't just super accurate, it's also practical. You see, unlike some other big AI models that need a ton of computing power and specialists to run them, these ensemble methods are way more efficient and give you straightforward guidelines. That makes them perfect for being used in real-world monitoring systems on actual dams. And that's really the big story here. This is a perfect example of how AI is breaking out of the digital world, of just analyzing images and text. It's starting to have a real, profound impact on our physical world, making the critical infrastructure we all rely on safer, smarter, and way more efficient.
You know, it really gets you thinking. If AI can help us perfect the design of a dam spillway, what's next? Could we have bridges that predict their own stress in real time? Or buildings that actively optimize their own energy use? What other physical structures out there could AI help us get just right?